recall that we said that if you want to turn a current on in a solenoid, then you have to put in a certain amount of energy. The work that you do is 1/2 L I squared. And I is the final value of the current. Now, notice that because of our use of the Ampere law, that we have I is equal to B over mu naught times little n. And I'm going to write that as I mu naught n h, where I substituted in the little n. And so I can write the work as 1/2 L B squared h squared over mu naught n squared. Now, we just calculated the self-inductance of the solenoid, and we had mu naught n squared pi r squared over h. And so our work becomes 1/2 mu naught n squared pi r squared over h times b squared h squared mu naught n squared. And did we skip a little square there? Because it's I squared. So we missed that mu naught squared. Now we've corrected it. And what we see here is we have 1/2. Almost everything cancels. The n squares cancel. We have 1/2 over mu naught, because we have a mu naught upstairs and a mu naught squared downstairs. And we have a b squared. So we'll put that like that. A b squared. And we have over here, one of the h's cancel. So it is h pi r squared. Now, in our geometry here, the volume is the height times the area. So what we have here is 1 over 2 mu naught b squared times the volume. And what we'd like to introduce is the idea of energy density, because what we're saying here is that the energy that we put into this system is being stored in the magnetic field. Just like in the capacitor, the energy was stored in the electric field. Here, whenever you have magnetic field, you have energy stored. And what we want to do is talk about an energy density, and there we'll introduce a quantity little u naught. Now, this is unfortunate that this u is not a mu. This is magnetic energy density. And it's defined by this calculation to be b squared over 2 mu naught for this simple case of the solenoid. Now, this result actually generalizes. And that's true in general, that's the energy density, even if you have a non-uniform B field. And our total energy stored in a magnetic field is the integral over the object, where there's non-zero magnetic field, of the energy density, mu. We don't need a mu naught here. That will just make life a little bit complicated. We have what we should really say is mu magnetic to distinguish from electric energy density. So we have the magnetic energy density integrated over the volume of the object. For our simple case of the solenoid, the energy is constant, and that's just b squared over 2 mu naught times the volume, and that's the result we have down here, h pi r squared. And so that's how we talk about energy stored in magnetic fields. When the magnetic field is non-uniform, like in toroids, we're going to learn how to calculate this energy density explicitly by integration.